Hello, and welcome to Pro Knowledge Station.
Today we tell the story of how Fourier solved the heat problem with waves. Imagine a metal rod heated on one end and cooled on the other. How does the temperature spread along the rod over time? This question changed physics and engineering forever. In the early 1900s, heat was a mystery. People could feel it, measure it, but describing how it moved through space was difficult. In 1807, Joseph Fourier studied how heat diffuses through solids. He proposed a bold idea. Any temperature distribution along a rod can be built from waves. That claim sounded outrageous at the time. Fourier's key insight was to describe how temperature changes both in space and in time. The mathematical model is the heat equation. It says the time rate of change of temperature equals a constant times the second spatial derivative. That second derivative captures how curved or uneven the temperature is, which drives heat flow. Here is the physical intuition. If one small part of the rod is hotter than its neighbors, the temperature curve has a big bend there. That bend means heat flows away, smoothing the curve. Over time, the temperature distribution smooths out. Fourier's breakthrough was to express the initial temperature curve as a sum of simple sine waves. Each sine wave evolves over time in a clean, predictable way. When you add them all up, you get the full solution. Mathematically, we write the temperature at position x and time t as a sum of sine waves with different frequencies. Each term has its own coefficient and decays over time due to heat diffusion. Here is a visual way to see the sum. The blue curve is a target shape. We add the green, orange, and purple sine waves. The sum moves closer to the target. This is the heart of the Fourier Series idea. Now notice what happens in time. High-frequency waves decay faster than low-frequency waves. This is why sharp temperature spikes disappear quickly, while large, smooth variations remain longer. That's the physical meaning of the exponential decay term in Fourier's solution. Fourier's ideas spread far beyond heat. Today, Fourier series and transforms are everywhere. In electrical engineering, we analyze signals and filters. In mechanical engineering, we study vibrations and resonance. In civil engineering, we model heat flow in buildings. In medicine, we reconstruct images in MRI and CT scans. And in audio, we decompose sound into frequencies. Let's connect it to a real engineering problem. Suppose a long metal beam in a bridge is heated unevenly by the sun. Engineers need to predict temperature changes to prevent cracking. Fourier's method lets them model the initial temperature profile, break it into waves, and see how it smooths out over time. This helps design safe materials and structures. To summarize, Fourier solved the heat problem by turning temperature into waves. Each wave evolves simply, and the sum solves the complex reality. This idea changed mathematics, physics, and engineering, and it's still essential today. Once you see the world in waves, many problems become beautifully solvable. We will solve the one-dimensional heat equation using separation of variables. We'll go step by step, build intuition, and end with the full Fourier series solution. Here is the one-dimensional heat equation. It tells us how temperature changes in time and space. Alpha is the thermal diffusivity. Let's picture a thin rod of length L. The temperature depends on position x and time t. We'll assume the ends of the rod are kept at 0 degrees. Step 1, we assume a product solution. We separate temperature into a function of x times a function of t. Now compute derivatives. The time derivative is x times theta prime. The second space derivative is x double prime times theta. Substitute into the heat equation. Now divide by alpha, x, and theta to separate variables. The left side depends only on t, and the right side only on x. Therefore, each side must equal a constant. We call it negative lambda. So we get two ordinary differential equations. One for time, one for space. The time equation is a decay equation. Its solution is an exponential that decays in time. The space equation is a simple harmonic equation. Its general solution is a sine plus cosine. Now we apply the boundary conditions. The ends of the rod are 0 for all time. First, t at x equals 0 is 0, which forces b to be 0. Then t at x equals L is 0, which makes the sine term vanish at x equals L. That gives us quantized values of lambda. So the spatial eigenfunctions become pure sines. Each mode has its own decay rate. Each mode is a product of the spatial sine and the exponential decay in time. Because the heat equation is linear, we can add all modes together. This gives the full Fourier sine series solution. The constants B sub n come from the initial temperature distribution. If we are given T of x at time 0, we expand that initial shape as a Fourier sine series. The coefficients come from orthogonality of the sine functions. The formula is B sub n equals 2 over L times the integral from 0 to L of f of x times sine of n pi x over L. Let's build some intuition. A single sine mode decays in time. The shape stays the same, but the amplitude shrinks exponentially. Watch the curve. Let's summarize. We separated variables, solved two ordinary differential equations, applied boundary conditions, and combined all modes using a Fourier sine series. This gives the general solution for the one-dimensional heat equation on a rod with 0 temperature at both ends.
Don't forget to like this video, share it with your friends, and subscribe to Knowledge Station. Thank you for watching.